Welcome to this video lecture. The goal of this lecture is to go over the time-distance diagram used in refraction seismology. So, if we consider seismic waves in the ground, there are three different possible pathways that energy can take through the ground on its way to our instruments. The first path is the direct wave. The direct wave, as the name implies, is the wave that goes directly from the energy source to our instruments through the upper layer. The next wave that we could consider is the reflected wave. This wave travels through the upper layer down to the boundary with the next layer and then reflects back up. Both the direct wave and the reflected wave are going to travel at the velocity of the upper medium. The final possible pathway for rays that are going to make it back up to our recording devices is the critically refracted wave, also known as the head wave. So the head wave is going to travel down through the first layer, hit the boundary at the critical angle, refract with an angle of refraction of 90 degrees up to the boundary between the two interfaces, travel along that boundary at the speed of the lower level, and then refract back up where it can be recorded at our instruments. So in order to pick out useful information from these different rays, the thing that we actually measure with our seismometers, we measure two things: amplitude and time. So we're going to spend a lot of this lecture talking about the time that it takes for waves to travel these three different pathways. So first, how long does it take to travel to the receiver for the direct wave? Take a second to think about how long you think it will take this wave to go from our shot, our energy source in the ground, to our geophone. To figure this out, you can actually use the equation for velocity, which is velocity equals distance divided by time. Solve that for time, and you have time equals distance divided by velocity, which you could write time, the thing you're recording at your seismometer, equals distance x divided by the velocity of the first layer. Now, if you were to then plot this, the time it took for the direct wave to reach the instruments, you would see if there were geophones at each of these distances, you would have the arrival times being later in time, the farther away from the instrument. That makes sense. And if you consider the equation for this line, velocity, if you wanted to know the velocity of the upper medium and you didn't know it beforehand, velocity is just 1 over the slope of this line on a travel time plot, which is also called a TX plot because it's relating time to distance, right? So what do? You send energy into the ground, wait for that energy to be recorded at multiple instruments, look at the output for each instrument, and when the energy arrives at each instrument, you measure what time it arrived at, you plot that, and then if you want to know the velocity of that upper layer, all you have to do is take 1 over the slope of that line for the direct wave. Now, for the reflected wave, we ask the question again, how long does it take to travel to the receiver? And more importantly, I'll ask, does it ever, well, hopefully you can just see that the reflected wave is always going to take longer than the direct wave, right? The direct wave travels the shortest path. The reflected wave is always traveling farther. They go at the same speed, so the reflected wave will always be farther back in time than the direct wave will. So if we were to plot that, now the direct wave is still on there, is the black line, and the reflected wave is that red sort of bending line that represents the timing of arrivals of the reflected wave. You can see that at very short distances where those reflections are going fairly straight down and up again, it takes significantly longer for those waves to be detected, but at very large distances, the reflected wave actually, the timing of that approaches the timing of the direct wave. Okay, so the red line is represents the timing of the arrivals of the reflected waves. And that just brings us to the critically refracted wave. So we can actually build up an equation that represents the travel time of our critically refracted waves. And it's going to look like this. Time equals 1 divided by the velocity of the lower layer times x plus some other factor that depends on the velocity of both of the layers. And it makes sense that it should depend on things like the thickness of the layer h. That's the thickness of the top layer, so that's going to help us determine how much time it's spent in this upper layer. And of course, we're going to need to know something about the velocity of both layers since it travels both at the speed of the upper layer, and then while it's along the boundary, it travels at the speed of the lower layer. So where does this equation actually come from? You could actually derive it from the velocity equation and trigonometric relationships. So the velocity equation, that's just, again, velocity equals distance over time. Reorganize that for time. And then the trigonometric relationships I'm talking about are sine, cosine, tangent. If you use those, for example, the sine of theta here, theta being the critical angle, would give you this segment of x along the top, which is going to be the same as this segment of x over here. So you could work out some of these relationships with that. And then the other piece of knowledge you're going to need is just your Pythagorean theorem. And armed with all of those equations, you could start from first principles of the geometry of this image and end up deriving this equation. We won't do that in this class. This is not an algebra class, but hopefully you are comfortable enough with algebra that you will be able to use this equation, as this is really important in seismology in order to help us determine the thicknesses of layers and the velocity of layers. Another thing to note about this equation is it's really just the equation of a line, right? So the thickness of the layer, that's a constant. The velocity of the two layers, those are constants, right? So everything over here on the right is just a constant. Nothing is changing here. As we let x increase, where that just means that we're moving farther along the profile. So this is just the equation for a straight line, y equals mx plus b, and that is y equals the slope times distance plus the intercept with the y-axis. Now, here it is plotted on the travel time graph, the TX plot, and it's labeled head wave, and you can see that it's, once again, it's a straight line. And you can also see that instead of going through 0, 0, it is intercepting our plot here with the y-intercept being the plus b part at the end of the equation, that constant. We actually call that the intercept time, right? So we can count the intercept time can be found by matching the equation for a line to our data here, and then you can back out the intercept line and use that, the intercept time, and use that to calculate thicknesses. Okay, and I will show an example of that, so hopefully you're not too confused yet. Important things to remember are just that the entire equation simply represents the equation of a straight line with an intercept that we call Ti, which is defined by that second half of the equation. Okay, so here it is all again, and you can see the ray paths on the bottom, and then the time for each of those ray paths to be detected by our seismometers, which are going to be geophones, is on the top. Things to note about this graph: you have the critical distance. This is the earliest that refracted rays can begin to arrive at the geophones. As you'll see, at the critical distance, they actually arrive later than the direct waves still. So the other thing that we often discuss in refraction seismology is the crossover distance. So this is the distance at which the refracted rays first begin to arrive ahead of the direct waves. Okay. Other things to note, if we consider only the first arrivals, right? So if we have an instrument here, well, let's say here, it's going to detect, so time's going on and no energy, no energy, no energy, and then that direct ray hits, and then more time goes on and the refracted ray hits, and then the reflected ray hits. And we can see all of those in the data. But if we instead choose only to examine our first arrivals, then we only plot the arrival times of the very first type of energy that arrives at our seismometer, then what we're going to get is a series of straight lines. And the first straight line here, okay, I'm going to erase that because my line isn't as straight as it should be. But that first line, that is going to have a slope equal to 1 over the velocity of the upper medium. And then if you notice, the second line is going to have a slope equal to 1 over the velocity of the deeper medium. And if you had a third level, then you could have another line with a slope equal to 1 over the velocity of that third level. If we consider the equation for the line, so this is the equation that's going to be describing this line here. And we set the time that we're interested in to be the intercept time, because this equation is true over the whole line, but the intercept time, we know what it is because we can read it off of our plot, right? So if the velocity is 1 over the slope, then the intercept time is the plus b, and we can get that just by determining the equation of the line. And once we have that, we can set it equal to this. And given that we know these two numbers, the velocities, we've taken those from the slopes, we can calculate the thickness of the line. So using that t-intercept time, we will be able to determine thicknesses. Also, note that reflected rays are never first arrivals. The seismic refraction method does not use reflected waves. We have a whole different way of utilizing those for information that we will discuss in the next chapter. Okay, so in practice, the goal of seismic refraction method is to determine the structure of the subsurface, the same goal as most of geophysics. Questions that we can begin to address include how many geologic layers are down there, what types of materials are down there. That is in some ways determined by the velocities, right? So different materials are characterized by different seismic velocities. And of course, these seismic velocities are actually a property of that material, right? So it's not going to change very much depending on the material that you are sending that energy through. And then, of course, the thickness of each layer. These are all things that we can calculate directly from the travel time plot. The method that we use, our instruments record the travel times of the direct and the critically refracted waves. We plot the first arrivals to determine seismic velocities, which tells us what type of material we have. We read the intercept time off the plot, which then we can use to calculate the thickness of the layers. And that gives us a more complete picture of the subsurface. So here, just to recap, you have all the different pathways that energy can take through the ground, how the first arrivals from each of those pathways is going to look on a travel time plot, and the equation for arrival times coming from critically refracted waves. So in the next video, we'll show you an example and get a little bit more detailed about how to actually do this with the real seismic data. See you then.